This nuclear bomb is called Little Boy, and this is the same bomb which destroyed Hiroshima in 1945. Now, you may know that nuclear bombs are made using uranium, but the question is why uranium? It turns out that uranium atoms are highly unstable. When a neutron hits a uranium nucleus, the nucleus splits in a process called fission. This produces two smaller atoms, a large amount of energy, and three new neutrons. The interesting thing about this process is the release of these three neutrons because they can hit more uranium atoms, causing them to split as well. So one reaction becomes 3, then 9, then 27, and so on. This rapid increase is called a chain reaction and it releases a huge amount of energy in a very short time, just like a bomb. Now, from this whole process, you must be getting an intuition that to make a nuclear bomb, you just need a block of uranium, and if you shoot a neutron at it, then it should explode like a bomb. But this doesn't work like that. Here's why. Uranium sometimes undergoes spontaneous fission, meaning it randomly splits and releases neutrons even without being hit. Now, this situation is more confusing because if neutrons are already there, then where is my chain reaction? To understand this properly, we first need to know that a piece of uranium can exist in three different states. The main difference between these states is that in some states the chain reaction can sustain itself, while in other states the chain reaction eventually dies out. Okay, I feel it's still confusing. Let's make it really clear. So, in the subcritical state, most of the neutrons produced simply escape before they can hit another nucleus. So, the chain reaction quickly dies out. Then comes the critical state, a perfectly balanced point where every fission event produces just one more fission on average. That means the reaction sustains itself, not growing, not shrinking, just staying steady. And finally, the supercritical state. In this scenario, more than one neutron from each fission goes on to cause additional fission events. The reaction starts growing exponentially, and that's when an enormous amount of energy can be released. Alright, imagine this tiny sphere of uranium. It's so small that any neutron created inside shoots straight out to the surface and escapes. This small sphere stays subcritical. Now we add more uranium and it reaches the critical state, the point where the chain reaction can finally sustain itself. But then we add just a bit more mass and the sphere tips into a supercritical state. Oh, supercritical mass is the nuclear bomb. So, to make a nuclear bomb, instead of throwing neutrons at uranium, we throw uranium at uranium, meaning we bring two subcritical pieces together to form a larger supercritical mass. Of course, not this way. Instead, we use something called the gun type assembly, where one piece of uranium is literally fired into another to create a supercritical mass. From this picture, you can probably get an idea of how this will work by looking at these three things: an explosive, a hollow cylinder, and a solid cylinder. If not, then it's really simple. When this bomb is triggered, conventional explosive fire that hollow cylinder down the barrel at tremendous speed. It slams into the solid piece, locking together and instantly forming one large supercritical mass. Surrounding this uranium core is a tungsten carbide neutron reflector whose job is to bounce escaping neutrons back inside. You can feel the effect of this reflector by looking at this simulation. You can observe that the reflector does not allow the neutrons to escape and it pushes the reaction to reach its maximum potential. Okay, so here we go. But now we have one more problem. In a real scenario, we are not going to have a control switch to ignite the explosive. Instead, the bomb is dropped from a plane and it needs to activate automatically. To solve this, nuclear bombs have a barometric sensor to measure the altitude, and when it reaches the correct height, the detonator is triggered, and that's it.